Welcome, everybody. This is the room for the medical track for the afternoon. My name is Irwin Barnes, and we have a series of speakers that will be handling many important issues in the medical area. Our first speaker is Adam Norton, who will be presenting to us an alternative approach for a Mars gravity simulator. Adam, thank you.
Thank you. Right. Good afternoon, everybody. My name is Adam Norton, and I'm an artist based in Sydney, Australia. Today, I would like to talk about the design and benefits of building a low-cost Mars gravity simulator. I will present some results and discuss my conclusions about future walking styles on Mars. I will also make a few brief comparisons with other types of Mars gravity simulator and make a few proposals for future testing in this kind of rig. Firstly, why do we need a Mars gravity simulator? Well, we need to design good spacesuits for exploring and working on the surface of Mars, and we need simulators to test how effective they are. The suits developed for Mars will be used for a number of years given the journey turnaround times involved and the impossibility of making any adjustments there. So they should be the very best they can be for the demanding work of exploration and habitat construction. Good suit efficiency also saves energy and oxygen, which extends exploration time and safety parameters, and of course ultimately reduces mission weight. Reliable and economic simulators will give many good minds the ability to contribute to suit design and Mars walking studies. Affordable access to good quality space science is good for the cause of Mars exploration by improving science outcomes and increasing public interest and knowledge. I'll have more to say about that point at the end. First thing is I want to show you some footage from astronaut Gene Cernan experimenting with walking styles on the lunar surface while talking to fellow Apollo 17 astronaut Harrison Smith.
Boy, when you do this, then you go down slope. That first step is a long one. I'm having... This is the best way for me to travel, uphill or downhill. What's that? Like this, two-legged hop. And on level ground, I can skip. I don't like that loping thing. Oh, the loping's the only way to go.
Checkpoint.
See, when I'm on level ground, I can skip. But this two-legged thing is great. Man, I can cover ground like a kangaroo.
Okay, so notice the astronauts talk about lopes, hops, and skips, and how different moves suited different conditions, as well as their own personal preferences for the moon. So, walking styles for the surface of Mars will be specific for Mars conditions. If you review more Apollo footage, you will note how the astronauts moved surprisingly fast and how often they fell over considering their extensive training. This image shows one of the Apollo type of lunar gravity simulators developed at Langley Research Center by Amos Spady Jr. and others for the Apollo series. This is known as an inclined plane simulator. Basically, the difference between Earth gravity and lunar gravity is taken up by the slings supporting the test subject at various points along the body, leaving the remaining weight through the inclined plane to represent the new weight of that same person on the moon. Film footage of these inclined plane simulators in action look very effective, and they received good reporters from experimenters at the time. Here is an uncomfortable-looking Walter Cronkite on the large inclined plane simulator installed on the moon crane facility at Langley. These types of inclined plane simulators run along a high, straight rail. Here's an overview of the moon crane at Langley in the 70s. The moon crane would have given a maximum travelling distance of 400 feet. But quickly, let's run through the math. The calculation for an inclined plane simulators must come from this classic diagram of the forces acting on an inclined plane. Because of the action on the slings, we can ignore the forces horizontal to the inclined plane. and we are left only with the forces through the inclined plane. Again, we are only interested in the change in the effect on Earth gravity, which turns out to be a value of the cosine of the angle of incline, theta. So, the calculation to simulate lunar gravity requires an inclined plane of 80 degrees off the horizontal, whilst Mars gravity, stronger than the Moon, requires the inclined plane to be just less than 68 degrees. For the Mars gravity simulator that I developed, I took the principle of the inclined plane simulator but made some simple adjustments. I substituted a fixed swiveling anchor point to support the ropes and slings instead of a long straight rail, and replaced the straight inclined plane for a circular cone or frustum, the red bit. This greatly reduces the size and cost of the rig, and it has two other advantages. Some reports from the Langley tests complained of a momentary delay in the start of a movement of the sliding rail when a test subject took a step, which could be off-putting. There is no delay with a swiveling anchor point. Secondly, a circular rig gives unlimited forward movement rather than the maximum 400 feet of the moon crane. A disadvantage is that to maintain the correct angle on the inclined plane, the height of the rig has to stay in the same proportion to the diameter of the frustum. That is about 22.5 to 1. I was given an opportunity to build a working prototype of this Mars gravity simulator by an arts organisation called Performance Space in Sydney in 2011. With a budget of just 3,000 Australian dollars, which is about 2,200 US, and a running time of 4 weeks, we set about testing and building the rig. This image shows me in a sling and support test. We use these tests to work out the best sling placements and to check the correct angle of the incline. The frustum was the most complex part of the build. Using a CAD program, we worked out the sections and the angles of the individual elements and had them cut out on a CNC router, then assembled them. This image shows the installation of the central 360-degree swivel and anchor point at about 25 feet, the maximum height this venue could accommodate. This dictated the size of the frustum. These are the frustum segments painted and ready for installation. For the rigging, we used a product called Dynex, super strong, lightweight rope, commonly used in the theatre and film industry. You can see the 5-point support rig. The head support is a ring bolt attached to a motorbike helmet. 2 swing seats support the torso and the hip, and a sling supports the upper leg around the knee. The most complex item in the rig is the dogleg brace to stop the bottom leg support rope interfering with the upper leg sling during the walking action. Okay, testing stations, various monitors and cameras and scales. This is an overview of the final arrangement. Please note the whiteboard to the right of the testing area to record results. Familiarising myself with the rig was remarkably straightforward. I found the rig very easy to climb into and out of and easy to get used to. It was much more comfortable than I had anticipated. Walking at this strange angle to the vertical does not present any balanced problems. With the rig ready to go, I decided to run a series of walking and moving tests. These included walking, jogging, and running normally like on Earth, also testing all of the methods used by astronauts in the lunar landing footage, and anything else I could think of trying. I'll now play some footage showing the kinds of testing procedure I would run through with the rig. All right, well, I'm just going to alternate from bounds to lopes, but just try and keep going for 10 minutes without stopping, basically.
Sure.
And just see. So if you want to count the laps,
yep, sure.
and you time me, then we should be good to go for the last test. So this is just going to be for 10 minutes. Maybe if you just call out every couple of minutes where we've got to.
Sure.
You know, so that after I know where we're getting.
Do you want to have some?
All right? Yeah. So,
Yep.
okay, on the red mark.
A bit forward. That's it.
Okay, Belinda, just want to say go. Checking the scales to sort of check that the weight came in right. During the program, I tested as many different walking styles and gaits as I could imagine. With each type of gait I tested, I tried to set an even pace, and I tried to find the most comfortable rhythm and as close to the target speed and the type of gait I was testing. It was instantly clear that some locomotive styles become harder or easier in simulated Mars conditions than in Earth gravity. You can see from the footage faster speeds have a natural fluidity. The test subject often adopted quite a long gait and stride pattern, while slower speeds at a more vertical stance are awkward and more difficult to maintain. At very high speeds, however, it became a bit more unstable, and I think there'll be some footage of that coming up. And this bit's a very nice and fluid move round the Frustum. But I think it starts to get faster and it starts to get a little bit more unstable. But I measured some of these strides at about, when I was at the very best, it was going at about 10 meters per stride. Or. Whew.
Well done.
Wow. I was in space, man.
I think I was in space as well.
I wonder how far I went. So that's 102 times 15, which equals 1.5K.
1.5K of running, that's not bad.
That's not bad. It's very easy. It's much easier. I couldn't run 1.5K in 10 minutes now, I don't think.
On Earth atmosphere?
Sorry?
On the...
Okay, so here's one of the results boards I obtained. Some of the tests were conducted over a fixed time period, whilst others were set over a fixed distance. To the right of the table, I marked each test for suit and gait comfort out of 5. Note also that the bunny hop common in the Apollo lunar footage was almost impossible at simulated Mars gravity. I only managed to complete one test at this gait style. I suggest Mars has too much gravity for this type of movement to be an effective method of locomotion. Right, my major conclusion from 8 days of testing was that a common locomotive gait will evolve for Mars, which will be generally faster than Earth walking pace, with large bounding strides with a lower centre of gravity. Another thing I noticed is that it is much harder to walk slowly on Mars because the weight to inertia ratio is different on Mars than for Earth. So at a slower pace, your inertia is more likely to topple you over. This might account for all the falls in the Apollo moon footage. I think we will see people develop swift, fluid strides, moving from one working area to another, with a lower centre of gravity, adding greater stability. A little bit more like a ballet move. Mars suit design will have to be much more flexible at the waist than current spacesuit types, enabling large, easy strides for best efficiency. Perhaps people can experiment with where they place life support services to help improve stability. Around the thighs might be better than on the back. Okay, of course, some of the problems with this Mars gravity simulator. Okay, so an inclined plane simulator only works forward or backwards, not sideways. Also, there is a rotational inertia component that creeps into the rig with faster speeds. It accounts for a small amount of extra acceleration as each footfall drops a little further around the frustum than would normally be the case along the flat. So the faster you go, the more inaccurate the rig becomes. Mind you, if you increase the size and height of the rig, this will reduce these effects, but it also increases costs. Jumping high increases the relative gravity on the subject as the angle of incline changes. However, there is also a pendular action that applies to the test subject as he or she returns to the surface of the inclined ramp. So I think this is less of a concern. Let's look at some other types of partial gravity simulators. Here's a vertical support offsetting partial gravity type. Weights and springs and servos are used to offset some of the Earth gravity. I suspect it is complex to predict the correct responses to the movements of the subject, and that they are also confined to a treadmill. During Apollo, NASA experimented with various vertical types of rig mounted on vehicles to overcome this issue. Here's another type of mechanical gravity assist. Again, it must have a complex feedback system with the test subject, again restricted to a treadmill, and only the midsection of the body in reduced gravity. Pressurized gravity reduction. This system uses air pressure applied to a flexible seal skirt around the lower body to produce a lower gravity effect. It's mostly used for patient rehabilitation. Note how this brand also uses a fixed treadmill. Okay, the vertical treadmill, currently favoured by space agencies. Again, this treadmill limits movement and has a difficult entry and exit procedure. This is mostly used for muscle and bone retaining exercises and space flight reconditioning. Low gravity, and here's the next one. Low gravity produced with parabolic flights, probably the most fun, but they have a short duration and high cost, and probably better for microgravity training and experiments. Of course, all types of reduced gravity simulators have their advantages and disadvantages, and they must be used fit for purpose. However, the type of Mars gravity simulator I'm demonstrating is very cost effective. The circular inclined plane type discussed can be built relatively cheaply within the budget of smaller organisations and universities and schools. Its inaccuracies, I believe, can be compensated for. No complex special equipment is required, the frustum and dogleg brace being the most complex parts. But everything can be sourced from the local timber yard, rigging companies, and any metal workshop could build the leg brace. Long durational movement. No distance or time limits on using this rig. It has a static walking surface rather than the treadmill. This surface could be made more realistic with the addition of some rocks and stones, and you could also push the frustum off-centre to simulate undulations in the Mars surface. It can be sized to fit into a small hall, sports hall, tall atrium or warehouse space. It's relatively quick to assemble and disassemble, with the frustum made in sections for storage. Improvements on my rig. The bigger the rig, the better the ride, and the more consistent the results. The limiting factor is the top height of the rotational anchor point. Other than that, there is no limit to the size of the rig. The simplest of rigs could be built from the top corner of a tall building, given some clear flat area below and some inclined slope. This could be used for vertical jump testing. Or a very tall tower could be used to support the swivelling anchor point, and the inclined plane could be made from packed earth and rocks piled into a ramp below. Okay, so future test objectives. Well, I think movement analysis further movement analysis has to be completed to work out what kinds of movements we'll do. Also, we need to figure out as much about the movement on the surface of Mars and how to adapt to it, especially over long time trials. Develop and test the most useful and reliable suit designs using input and ideas from many interested parties. Use the simulation device for training and working with auxiliary devices such as heavy packs and handheld and operated equipment. Now, for my final comments, I'd like to say that as an artist with a long-held interest in space exploration, the dissemination of scientific knowledge through all levels of society and interest groups is fundamental to our future progress. It is apparent to me that there is a widening gap between ordinary citizens and the modern scientific world. I think this is based on a fundamental lack of understanding about the processes of scientific discovery, and this is paralleled in the poor understanding of science in our political leadership. Perhaps it has always been there, but I think it might have deepened in the middle of the 20th century with the secrecy surrounding big science projects like the nuclear bomb. However, by re-engaging ordinary citizens in real interesting science with tangible outcomes that can directly affect real issues, we can help bridge that gap. My ambition in the future is to be involved in the development of such objectives. I'd be interested to hear your thoughts and discuss opportunities. Thank you. Any questions? Yeah. Hi, yeah.
Do you have any plans to pair your rig with, say, a VR environment?
That would be good. I did do some filming with the rig, wearing the rig, but you could obviously extend that with some kind of VR, but that's beyond this. Yeah, that's.
Pair your up and down with some of the training, walking through the training.
Absolutely, and you could paste the environment in there, couldn't you? So you could knock out the slightly strange effect of going around in circles. All right.
Okay, when you're going faster, you said you're getting into some issues. Is it due to the equipment, or due to your lack of experience in that, or do you think it's not something you'd be doing so fast on Mars?
Well, I think it was only getting unstable when I was running at close to a sort of slow sprint, which probably isn't a sensible decision on Mars anyway. But I think that the inaccuracies of the rig are increased because the inertia is increasing. So I think that was making that problem a little bit more obvious. But with a bigger rig, I think you're going in a much less tight circle, and so you can overcome that problem.
Have you put anybody in it as like a martial artist or a dancer to see if they have a different?
No, absolutely. I think with this rig, anybody could build one, and many people could test anything that they fancied. With different kinds of people and experimenting with different ways. This was just a one-off prototype that I got to use about 8 times. 8 test sessions with.
Problem with dizziness, disorientation, inner ear?
None at all. It was just so sweet to just step into, and you got it straight away. At the back.
How easy would it be for some kid to come off the street and try it out? How much training would they need?
None at all.
So you could take it around the country.
Yep.
Demonstration.
Yeah. No, I mean it. I was surprised. I thought I might have to get used to it, but all I had to do was get used to not getting too enthusiastic and falling on my head. That was all.
You mentioned, of course, having a lower center of gravity. I'm
Yeah.
wondering if that's something that you did consciously by bending your legs a little bit more, or how? Because
Yeah.
So would that differ from men and women, or is that something that you moved your body in order to lower?
That would be great to find out, just explore. I mean, I think the lower centre of gravity is natural because you weigh less and you're stronger. You can spread your legs further and you just can hold yourself in a slightly lower place than you would sensibly on Earth, Anybody else?
We're talking about, you got a little excited and fell over the same mass and a lot less weight. Is that what you get used to?
Well, yeah, I mean, that's...
Stopping when you're going that fast and you won't weigh it as much, but you have as much mass.
Well, exactly. I mean, you have the same inertia. So you've got that you do in regular gravity, in Earth gravity, but you've got less mass on Mars. So, you're in a slightly more unstable position than you're used to because your inertia will pull you over, even though you feel the forces are less. I think you just have to get used to it. But I think with the lower centre of gravity, I think that compensates for it because, of course, if you're down here, you're less likely to tip over.
I wonder if you thought about that. You were in 1G condition when you did this.
Yeah.
Your musculature was at a 1G level.
Absolutely.
You were moving instantly to a 1/3G.
Yeah.
So I wonder over time, if we imagine someone actually in that environment,
Yeah.
I wonder what the effect would be because they're probably going to change their musculature.
Absolutely. For people, living on Mars, that will happen. But of course, our problem is the next 5 to 10 years, really, isn't it? Short durational visits.
Thank you.
Okay, thank you.
Thank you so much.